Well, hello. So, as some of you have noticed, there were some sound issues with the previous version of this video, so I'm going to re-record this. So, this is a little bit of a Frankenstein lecture because I'm going to use the slides from the previous one and talk through it again. So, this video is about intermolecular forces. This is kind of the first step in understanding how do chemicals interact with each other, how do they react with each other. We're going to start with the simplest case, and where we're going to keep all the molecules the same. So, we're going to have nothing but water molecules interacting with other water molecules and fluorine molecules interacting with other fluorines and so on and so forth. And we're going to start with that simplest case, and then we're going to build up from there. We're going to make things, we're going to start to look at what happens if you have water molecules and fluorine molecules in the same thing, and how does that work? And that's where we're going to go get into chemical reactions, right? So we'll start with the simplest case today and build up from there. So when we talk about intermolecular forces, what we're really talking about is why are molecules the things that they are? Like, why are molecules gases or liquids or solids, right? And the reason is it depends on how fast those molecules are moving and how much those molecules kind of stick together, right? So, um, if you have molecules that stick together really strongly and they don't allow the molecules to move around, that means that you're going to have a solid, right? If you have molecules that have almost no interaction with each other, so they don't stick together, they just kind of bounce off each other, and they have a lot of kinetic energy, they're moving around very fast, and you're going to have a gas, right? And then in between those two is the liquid, right? A liquid is something where the molecules do attach to each other and they do stick together, but they still have a fair amount of freedom of movement, and so you have a little bit more kinetic energy there. So liquids are kind of that in-between case. But when we talk about why are some molecules liquids and some gases and some solids, there's two factors, right? So two factors. The first factor is molecular weight. Right? So the heavier a molecule is, the slower it's going to be. And so a light molecule is going to be able to fly around. It's going to have a lot of kinetic energy. It's not going to have, it's going to be really hard to have interactions between those molecules just because they're moving so fast. Right? So lighter molecular weight compounds tend to be faster. Lighter molecular weight compounds tend to be gases. Now there are exceptions to that rule. We'll talk about that when we get to the second point. All right. So the second point is intermolecular forces. Right? So molecular weight is number one. Number two is intermolecular forces. That's the one that we're really interested in. That's the one that we're going to spend this video talking about. Right, so intermolecular forces are kind of how sticky are those molecules. If you have two molecules in the same area, do they attract each other or not? And the stronger those intermolecular forces are, right, the more attractive they're going to be, the more they're going to hold those molecules in place, and the more likely you are to have a liquid or a solid. Right? And so we're going to talk about water as our example. Water is a great example because water is very low molecular weight, right? There's only 3 atoms in it, and they're not very heavy atoms. And so you would predict that most molecules that are around the same molecular weight of water are gases at room temperature and standard pressure. But of course, water is not a gas at standard temperature or pressure. And so why is that? And of course, the answer is it's not molecular weight, it's the other one, it's the intermolecular forces. All right, so intermolecular forces. Let's see if I can get this thing to switch slides on me. All right, so stronger intermolecular forces equals slower molecules. This is just what we talked about, right? The stronger these forces are going to be, this is going to slow things down. It's going to make things into more likely to be solids, liquids, gases. It's going to make them more likely to interact with each other instead of just flying around. This is what I just said, right? Gases are going to be the fastest molecules. They're going to have the least strong intermolecular forces. They're going to have the weakest intermolecular forces. And then liquids are going to be stronger intermolecular forces, and solids are going to have the strongest intermolecular forces that we're going to see. Right, so if we're just looking at a scale here, this is kind of what we're going to see. All right, when we talk about intermolecular forces, what we're talking about are dipoles. So dipoles are, this is the this is a new idea, this is a new concept that we're going to use to discuss intermolecular forces, right? And what a dipole is a dipole in a covalent bond, the electrons that are part of that covalent bond, right? Every covalent bond is 2 electrons. Those electrons aren't shared evenly. So if we look at water, I've drawn water right here, H2O, right? We have 2 covalent bonds. We have this hydrogen-oxygen bond, and then of course another hydrogen-oxygen bond on the other side. And in those covalent bonds, those electrons, those two electrons that are part of this bond, are not just hanging out halfway in between the oxygen and the hydrogen. And the reason they're not is because oxygen and hydrogen pull on those electrons differently. And that is electronegativity, right? So if you have this covalent bond, you have oxygen, which is a very electronegative element, bonded to hydrogen, which is not electronegative. Quick review. We have our periodic table here. We have hydrogen up at the top, element 1. We have oxygen over here, element 8, right? And electronegativity increases as you go to the right of the periodic table, increases as you go up the periodic table. So the most electronegative elements are up here in this kind of upper right corner. Oxygen is right there. Oxygen is very electronegative. Hydrogen is on the other side, not very electronegative. And so what electronegativity means is that oxygen wants to pull those electrons toward itself. And so when oxygen and hydrogen are connected in a covalent bond, those two electrons are not halfway in between the oxygen and the hydrogen. They're being pulled towards the oxygen. And now electrons have negative charge, and so that has a consequence. The oxygen becomes partially negative charge, right? It has a partial, so we use this lowercase delta with a negative charge to show a partial charge. So we have partial negative on the oxygen, and then of course the result of that is partial positive on the hydrogen, right? The hydrogen is losing those electrons, the electrons are getting farther away, and so the hydrogen becomes positive. Electrons are negative, so the oxygen is negative, and it holds the electrons closer, right? That's what being electronegative means. And so if you connect an electronegative element and a non-electronegative element, we're going to get a dipole. And the dipole is just this uneven sharing, and we always see these partial charges, a negative and a positive, whenever we have a dipole. Okay, so what happens if we have more than one water molecule, right? So each water molecule is going to have these delta minus, delta plus, delta plus, delta minus, delta plus, right? All the hydrogens will be partial positives, all the oxygens will be partial negatives. And of course, what happens is if you have a partial negative in the vicinity of a partial positive, they're going to attract each other because opposite charges attract. And if you have a partial positive in the vicinity of a delta negative, they're going to attract each other. And so these opposite partial charges attract each other and create this kind of stickiness, right? The stickiness that we were talking about that are these intermolecular forces. They create this attractive force between a partial negative and a partial positive. So these opposite partial charges attract, and that is what holds these water molecules a little bit tighter together. And so instead of being water molecules that are gases, where they just kind of fly around and they bounce off each other and they never interact, when two water molecules run into each other, the minuses line up with the pluses line up with the minuses. We get this attractive force, and it holds them just a little bit tighter. And when you do this over and over again with billions upon billions of water molecules, right, you get enough interactions and enough attractive forces that the molecules slow down enough that we get a liquid instead of a gas. Right? So when we talk about chemicals, molecules, chemistry molecules, whatever we're calling them, right? When we talk about those, one of the things that we're going to look at is, do they have dipoles in them? Because if they do have dipoles, then they're going to have stronger intermolecular forces, and then we're going to have to think about when these molecules are attracted to each other, how do we get them to attract to other chemicals in our reaction, or are they going to be attracted to that? And what happens when we mix these things together? So we're going to get to solutions, which is later in the week. We're going to get to phase changes. How do we go from gas to liquid to solid, and those kinds of things. And then we're going to talk more about dipoles. So dipoles are kind of the base idea that this whole week is based on, and then we're going to apply it to a couple of different things. Okay. So the next one is all about dipoles. We can dive a little bit more into what types of interactions we see. We saw one example today where or in this video where water molecules interact with each other. But we're going to rank them. We're going to say here are strong dipole interactions, here are weak dipole interactions, and how do we recognize which one is which. So that's going to be the next video, which I get to re-record because that one also had no sound. So hopefully you'll get to see all these. Thanks.